Okay, this will be the last of our carbon nucleophiles adding to carbonyls. This is a little bit of a different reaction. There's kind of an additional step after the carbonyl addition, so there's a little bit more to figure out. That makes the mechanism a little bit more complicated, but the products are very easy to figure out, and so you'll see what I mean here as we jump to the reaction itself. So this reaction was discovered by a German chemist. Uh, in German, W's are pronounced as V's, or so I've been told. And so this is the Wittig reaction. The Wittig reaction starts with an aldehyde or a ketone. I'm just going to use an aldehyde. We'll use a simple one. And you react it with a compound that has 3 benzene rings. So I'm going to abbreviate, I don't know, I never remember if this is something that people know or not. But pH stands for phenyl ring. A phenyl ring is a benzene ring with 1 group attached to it. So basically what this is a phosphorus with 3 benzene rings attached to it. And rather than draw out all 18 of these carbons, we just write 3 phenyl groups. So pH 3 is 3 benzene rings, and those benzene rings do not participate in this reaction. They just hang out. So I'm just going to draw, I don't know, let's do a 6-membered ring like this. So this is a positively charged phosphorus, is reacted with this, and then what we do is we treat it with a very strong base. And so we're going to use butyl lithium. So if you recall when we talked about organometallics, we mentioned butyl lithium as one that's pyrophoric. It can start on fire when it's exposed to air and all this other kind of stuff. And the reason for that is it's incredibly, incredibly basic. It's very, very strong base, and which normally, for most things, we don't need a base that's that strong. For the Wittig reaction, we do. And so we need an incredibly strong base, stronger even than things like LDA, stronger than things like sodium hydride. So they were really pulling out the big guns as far as acid-base chemistry goes. Well, the butyl lithium does, so got a couple of notes up here. Butyl lithium is 1, 2, 3, 4 carbons with a lithium on it. And the answer is this is an extremely good base. And the reason that we need such a good base is because we are going to remove a carbon-hydrogen bond, right? So the acid, the most acidic hydrogen on this phosphorus compound is this hydrogen right here. And so butyl lithium comes in, removes that hydrogen, and makes a negative charge on the carbon. So we're just making the conjugate base. This is just a standard acid-base reaction. It's just kind of a weird one because both components of the acid-base reaction are kind of things we haven't seen before. This type of compound where you have the positive charge and the negative charge kind of next to each other but not really interacting with each other, this is called an ylide, Y-L-I-D-E. And this is, I mean, just we got to call it something. And the thing to know about the ylide is that it is a carbon nucleophile. Right? The carbon has negative charge on it, and that makes it a good nucleophile. If we have a good nucleophile and we have a carbonyl around, you can kind of guess what's going to happen, right? The carbon nucleophile will add to the carbonyl carbon, will break the carbon-oxygen pi bond, will create a lone pair on the oxygen, and that's going to give us the following. I'm going to drop this. This hydrogen is still here, but I'm not going to show it anymore because it's going to get in the way. We still have our 3 benzene rings attached to phosphorus, and on the other side we have our 6-membered ring. Okay, so again, we're using kind of unorthodox reagents, but this is just like every other carbonyl reaction you've seen so far, right? If this was H-, we'd see the same thing. It's just that this time we're bringing a lot more stuff along with us, right? We're bringing the ylide, we're bringing the phosphorus, we're bringing these other 6 carbons as well. Now, oxygen is negatively charged. Oxygen oxygen wants to be neutral. Phosphorus is positively charged. Phosphorus can expand its octet and accept more electrons, and so that's exactly what it's going to do, and we are going to make a 4-membered ring. Which makes everything nice and neutral, but it's also a 4-membered ring, which isn't great. This is one of my favorite chemistry terms. This is an oxaphosphatane. Again, that's not a term you're going to ever need to know, but it's fun to say, oxaphosphatane. So now I get to say it a bunch of times. So this oxaphosphatane here is we've made everything neutral, but we've introduced a huge amount of strain because of course everything is in a four-membered ring. And so what's going to happen is we're going to start breaking some bonds to get rid of this stuff. The oxygen and the phosphorus are very fond of each other. They overlap very nicely with each other electronically, and so they are going to stay together. So we're not going to break the oxygen-phosphorus bond, but we are going to break the carbon-oxygen bond and bring those electrons up there. And then this phosphorus can't accept too many more electrons, so it's going to give up some electrons too. And this way, everything stays neutral, and we end up with triphenylphosphine oxide, which is a byproduct, and actually a really annoying one, but that's neither here nor there. It's hard to remove. And you're going to make an alkene. And this alkene is the final product of the Wittig reaction. Right? So the Wittig reaction will take an aldehyde and a phosphorus compound like this one, and that is going to make an alkene. And you'll notice that if we split this double bond in half, right, this side of the molecule came from the ylide, and this side of the molecule over here came from the carbonyl. Right? And so really what we're doing here is we're just stitching these two compounds together, and then we lose the oxygen, we lose the phosphorus, and we end up with a double bond that connects them. Right? So we can kind of go, I can give you any carbonyl, so let's go back to our old friend acetophenone. And then some we'll just do something like this, right? This is a Wittig reaction. We've got the phosphorus in there, we've got the butyllithium, we've got a carbonyl. These are the three things we need. Without drawing the mechanism, right? You don't have to draw out the oxaphosphatane again, right? Or the ylide or any of that stuff. Without drawing any of that out, we know kind of what are the components going to be of our product. It's going to be this carbonyls attached to the ylide carbons here. We're going to lose the phosphorus, we're going to lose the oxygen, and there's going to be a double bond in between them. So we can kind of redraw this. This over here has 8 carbons, this ketone, right? It's got 6 in the benzene ring plus carbonyl carbon plus a methyl group. And this one has 7 carbons, 6 in the benzene ring plus this carbon right here, right? And so we can draw the final product here. Here's our 8 carbons there. And here's our 7 carbons on top, right? We've got 7 carbons up here. And we've got, if I can circle this, we've got 8 carbons down here. So without drawing a single mechanism, without drawing any curved arrows or anything like that, I can predict the product of a Wittig reaction, right? Which is a nice skill to have. It's important. We don't want to have to draw out every intermediate every time we want to figure out what the products of our reactions are going to be. And of course, you can go the other way too. If I say, well, all right, smarty pants, give me a reaction that will make the following double bond. Right, and let's do this, and then on this side we'll have a 5-membered ring. So you can look at this and you can say, all right, well, there's a double bond here, so one of the ways I know how to make a double bond is a Wittig reaction. So I'm going to split this way, and on this side I have 1, 2, 3, 4, 5 carbons, and on this side I have 5 carbons. The two components that I'm going to need are, well, one of them is going to be a carbonyl, and one of them will be the ylide, the phosphorus compound. So in this one I've got 1, 2, 3, 4, 5 carbons. In this one I've got 5 carbons. These two together plus butyllithium will get me to that final product. Okay. All right. What else do I need to say about the Wittig reaction? How to make the ylide. Right. So we can take, let's take the ylide that we just were trying to make, although it really doesn't matter too much. If you want to make this, the way that we make this is we start from triphenylphosphine and an alkyl halide, and it just does an SN2 reaction. SN2. Right? So triphenylphosphine attacks the carbon, we lose the bromine, and we get the triphenylphosphonium here. And then you treat that with a strong base, butyl lithium, and you end up with the ylide compound. We always take the hydrogen from the carbon right next to the phosphorus, because of course that's going to be the most acidic, because we want our negatives and our positives to be near each other so they can stabilize each other. Okay? And so we always take the hydrogen from the position right next to the phosphorus, which means whatever position we want to attach to our carbonyl, we want that to be where our leaving group is, because we can do the SN2, we can treat it with butyl lithium to make the ylide, and then we treat that with a carbonyl, and that's going to give us our alkene, whatever, 1, 2, 3, 4, 5, right? Whatever else we have over here, right? R and R, depending on what our carbonyl was, right? We can make whatever. So we can start with the bromide, convert it to the phosphonium, and then make the ylide and react it with the carbonyl. So that's the Wittig reaction. There's a couple of examples of that that I'll pass along to you so you can practice that. But that's the last of our carbon nucleophiles adding to aldehydes and or ketones reactions that we're going to talk about. So enjoy that. We're going to come back to ketones and aldehydes when we talk about enolates, but for now, as far as addition reactions where nucleophiles add to carbonyls, we've pretty much covered it. So what I recommend is just make sure you go through, make a list of all the things, all the reactions that involve aldehydes and ketones, right? We have reductions, so lithium aluminum hydride, sodium borohydride. We have H minus as a nucleophile, right? We have oxygen additions, so things like hemiacetals and acetals. Right? We have, and there's a fair amount of stuff there, right? Different reactions, different mechanisms, all that kind of stuff, so make sure you're comfortable with that. We have nitrogen nucleophiles, so making aminals, making imines, right? You'll notice that a lot of these end up being the same thing, where the nucleophile attacks the carbon, and that's it. And then we have, for carbon nucleophiles, we have cyanohydrins, we have Grignard reagents, or organolithium reagents, organometallics in general. So we have cyanide, we have organometallics, we have terminal alkynes, and now we have the Wittig reaction. So we have a few carbon nucleophiles to worry about as well. But all of these follow the same idea, right? All of them have the nucleophile adds to the carbonyl carbon, breaks the carbon-oxygen pi bond, it pushes those electrons up to the oxygen and makes a new lone pair. So that's the common thread that we're pulling through this entire chapter. And as we go on, you'll see that this continues to be the theme. So watch for that in the next ones, and enjoy.